practices resources reviewed and selected by technical experts. Today's webinar agenda is centered around the presentations from our guest panelists, Jan Tanvez and Dimitris Mentis, who have joined to discuss the Electrification Pathways application. Before we jump into the presentations, I'll provide a quick overview of the Clean Energy Solutions Center. Then, following the panelists' presentations, we will have a question and answer session where the panelists will address questions submitted by the audience. At the end of the webinar, you'll be automatically prompted to fill out a brief survey as well, so thank you for taking a moment to respond. The Solutions Center was launched in 2011 under the Clean Energy Ministerial. The Clean Energy Ministerial is a high-level global forum to promote policies and programs that advance clean energy technology, to share lessons learned and best practices, and to encourage the transition to a global clean energy economy. 24 countries and the European Commission are members, covering 90% of clean energy investment and 75% of global greenhouse gas emissions. This webinar is provided by the Clean Energy Solutions Center, which focuses on helping government policymakers design and adopt policies and programs that support the deployment of clean energy technologies. This is accomplished through supporting crafting and implementing policies relating to energy access, no-cost expert policy assistance, and peer-to-peer learning and training tools, such as this webinar. The Clean Energy Solutions Center is co-sponsored by the governments of Australia, Sweden, and the United States, with in-kind support from the government of Mexico. The Solutions Center provides several clean energy policy programs and services, including a team of over 60 global experts that can provide remote and in-person technical assistance to governments and government-supported institutions, no-cost virtual webinar trainings on a variety of clean energy topics, partnership building with development agencies and regional and global organizations to deliver support, an online library containing 5,500 clean energy policy-related publications, tools, videos, and other resources. Our primary audience is made up of energy policymakers and analysts from governments and technical organizations in all countries, but we also strive to engage with the private sector, NGOs, and civil society. The Solutions Center is an international initiative that works with more than 35 international partners across its suite of different programs. Several of the partners are listed above and include research organizations like IRENA and the IEA, programs like SE for All, and regionally focused entities such as the ECOWAS Center for Renewable Energy and Energy Efficiency. A marquee feature that the Solutions Center provides is the no-cost expert policy assistance known as Ask an Expert. The Ask an Expert service matches policymakers with one of the more than 50 global experts selected as authoritative leaders on specific clean energy finance and policy topics. For example, in the area of rural electrification, we are very pleased to have Ibrahim Rehman, Director of Social Transformation Division, serving as one of our experts. If you have a need for policy assistance in rural electrification or any other clean energy sector, we encourage you to use this valuable service. Again, the assistance is provided free of charge. If you have a question for our experts, please submit it through our simple online form at cleanenergysolutions.org/expert. We also invite you to spread the word about this service to those in your networks and organizations. Now I'd like to provide brief introductions for today's panelists. First up is Jan Tanvez, who's an energy specialist at the World Bank. His work focuses on energy access strategies globally and large-scale renewable energy investments in sub-Saharan Africa. Our second speaker is Dimitris Mentis, who is a lead researcher at the Division of Energy Systems Analysis at KTH Royal Institute of Technology. His work focuses on linking geographic information systems and electricity planning to estimate investment and capacity needs to provide access to electricity to the unserved. Now, with those introductions, I'd like to turn it over to Jan. Jan, perhaps you're on mute.
Good morning. Can you hear me?
Yes, thank you.
Okay, fantastic. Good morning, everyone. My name is Jan Tanvez. I'm an energy specialist at the World Bank Group based here in DC. I'd like to thank Stephanie and Eric for the organization of this webinar. Before we jump into the topic of today, which is a training on a new advanced data analytics called Electrification Pathways, I'd like to provide a bit of context to the role of data and analytics in the energy sector, as well as to introduce a new open data and analytics program that we're developing here at the World Bank. So, as you know, as you may have seen, data is everywhere. It's popping up to a lot of the press lately. It's always mentioned as a key driver of the digital economy and the way forward. This is extremely relevant for the energy sector particularly, and increasingly relevant for development. Key drivers of such transformation are as follows: an exponential availability of data. To start with, it is estimated that by the end of next year, the world would have created as much data as it has created until today. This is driven by the Internet of Things and more connected devices that create data in a real-time basis. In the same time, we're seeing an increased computational power and especially and increasingly into the cloud, allowing to extract more information from this exponential amount of data. Software capabilities go hand in hand with this computational power and are also increasing fast. And complex algorithms are emerging to respond to specific questions thanks to data and analytics. Open source algorithms are even more impactful in the sense that anyone can reuse them. So all those long-term drivers create opportunities in various sectors. Opportunities of cost savings thanks to analyzing such data, time savings as well. It brings new insights often that were difficult or impossible to extract before. They also can drive operational efficiency when data and analytics are used in real time to drive businesses processes. When it comes to the development work and development context, data and analytics are on a different pace. If you work in developing country, you might know that data to start with is often an issue. We often face a situation where there is no or limited data, where data is of poor quality when it's available. And we see also a phenomenon that is fragmentation of data, where data can emerge from various sources, making it difficult to compare and to use for the end users. In terms of analytics, whereas investment in data analytics never been that high in developed economies, in developing countries, they are pretty low, meaning that governments, public and private sectors do not invest as much into developing analytics that answer developing countries' questions. The number and capabilities of firms working in those markets are also limited. And finally, the government's capacity, which is of interest particularly to the World Bank, to analyze and leverage data analytics is fairly low. This reinforces a phenomenon that is called today as digital divide, making it increasingly difficult for developing countries to leverage the digital revolution, as some call it. So as I was mentioning, open data and analytics is critical, is becoming increasingly critical to the development agenda. It can help on various fronts, including strategic level decision making, but also investment identification and policy and regulation design. It serves as a private investment incentive and help private sector decision. This is particularly linked to the availability of data in markets, de-risking investment. It can lead to more accurate and dynamic infrastructure planning, and that's one key element of today's presentation. as well as operational efficiencies, and finally, transparency. Overall, what we're looking at is how data and analytics can help take better, faster, cheaper, and more transparent decisions. So the World Bank Group has developed a new energy sector open data and analytics program, which has for high-level objective to accelerate progress towards Sustainable Development Goal number 7 of universal access to clean energy through improved access to data and analytics. The program lays on or launched a new open data and analytics platform in last April 2017. It's a platform that is solely focused on the energy sector and on SDG 7. It takes a partnership approach to make more data and analytics available, with having so far 14 partners, including the UN, the World Resource Institute, Facebook, Bloomberg, Berkeley. All the logos are on the slide at the bottom of the slide. So far, those partners have contributed more than 300 data sets on developing countries that were not available before. Those data sets are available for free on an open Creative Commons license and available for all to use. Those data sets include, for example, more than 50 electricity grid maps, including one for every sub-Saharan African country. While data is great, the availability of analytics to extract information and knowledge from data is also important. And the website and its partner made available already 10 data analytics apps that draw on this open data in order to provide analytics tool for end users. So far, it accumulates 60,000 users from 153 countries. In terms of data, I took a few examples of the type of data that are available on the platform. So you can see on the right-hand side, for example, an electricity transmission and distribution grid map of the sub-Saharan Africa continent, which is today the most up-to-date and complete open data set on electricity infrastructure in Africa. The World Resource Institute contributed, for example, a data set with mini-grid locations in Tanzania. What you can see on the bottom right side is a map, a data set, comprising of all the mini hydro potential sites present in Madagascar, very useful for private developers as well as for the government. You have on at the bottom of the screen a high-resolution settlement layer provided by Facebook. In that case, looking at Burkina Faso and providing structures and settlement as a 30-meter resolution. Very important for designing, for example, access program, as well as citing renewable energy power plant where land and settlement can be an issue. It has also more traditional data sets, and you can see in the middle left of the screen, for example, a key flagship data set of the World Bank, which is the Utilities Technical, Financial, and Tariff Database for all African countries. In terms of data analytics, I'll go over fairly quickly. They're all available on the platform, and I encourage you to look at them. But to give you an example, we have a least cost electrification strategies, which looks at providing scenarios for universal access for every sub-Saharan Africa country, as well as Latin America. India Nightlight is an analytics which is highly innovative, looking at satellite imagery to identify progress on rural electrification using night lights data. The off-grid market opportunity is a tool available for Africa that crunches various geospatial layers to provide a high-level overview of what could be the market of the opportunity for off-grid solution in every sub-Saharan country. The Global Solar Atlas is an application that provides you with solar radiation measurements for every part of the globe in a couple of clicks. Climatoscope gives you an overview of clean energy policies for the globe as well, and a comparison between them. RISE is similar. We have an application focused on Myanmar, provided by the René Lemoine Institute in Germany, that provide information on off-grid markets in Myanmar and their potential. The global tracking framework, it's a visualization of progress towards SDG 7 globally. And the Africa Grid Explorer lets you explore the electricity grid infrastructure in Africa. Most of the analytics available on Energy Data Info are made available on an open source manner. Open source meaning that users have open access to codes that are free to modify and reuse. This supports innovation in the space as well as transparency. Innovation because if a researcher or a firm wants to build on an analytics that have been developed and build on the development work that have gone into developing such data analytics, can do so and not start from scratch, but already improve in what is already existing. A small case study, and this will be my closing slide, to introduce the electrification pathway application that was used by the government of Zambia in recent months. Basically, choose the electrification pathways to inform their country's strategy for electricity access. The government of Zambia has 96% of the population without access to electricity, but didn't have any least cost plan that could provide them with information on the type of technologies that could help the country achieve universal access at a faster pace. By using the tool that we're presenting today, the government was able to recenter the strategy on the development of off-grid solution for the country. And that's mainly due to the fact that the country is very sparsely populated, and therefore off-grid solution made sense for them in order to achieve faster progress. All in all, it saved them 3 months toward developing their new electricity access program, as well as additional resources that they could have needed to deploy to get that information. While this is a preliminary step to elaborating a strategy, additional data collection and modeling is now planned to improve on the plan that was provided to them and identify specific investment that will be part of such a program. So I will stop here and hand over to Dimitris to present us the tool and explain us how it works. Thank you.
Great, thank you very much. Dimitris?
Hello, everyone. Can you hear me?
Yes.
Okay, let me set up the presentation. Excuse me for that.
Yeah, no problem at all. Looks great.
Okay. Can you hear me well?
Yep.
Okay, perfect. So hello, everyone. It is a pleasure being virtually here, and many thanks to Clean Energy Solutions Center for hosting this webinar. My name is Dimitris Mentis, and I'm working at KTH, the Royal Institute of Technology in Stockholm, Sweden, and more particularly in the Division of Energy Systems Analysis. Jan has just introduced the importance of open data and analytics for energy access, and I couldn't agree more. EnergyData.info is a significant initiative that has already created ways for practitioners to share aggregated, updated, and publicly available data, reducing high transaction costs of data aggregation. And this in turn has helped us in mainstreaming the use of geospatial analytics for the energy sector. Moving towards open data and analytical tools, we have developed together with colleagues and partners an open source electrification tool that aims to identify investment and capacity needs for providing electricity to the unserved. And why is that? Well, nowadays we have around 3 billion people that do not have access to modern energy services and almost 1.1 billion people that lack access to electricity. The vast majority of these people are located in rural areas in sub-Saharan Africa, developing Asia, and some parts of Central and South America. They rely exclusively on traditional fuels to cover their daily energy needs, which in many cases causes harmful effects to themselves and their environment. This calls for a shift towards sustainable forms of energy. The tool we have developed focuses on electricity, as it can be easily converted into other forms of energy, such as heating, lighting, and mechanical energy, and can be easily transmitted from one place to another with the help of conductors. Early electrification is proven to be a key enabler for socioeconomic development. Several studies point out that the level and the quality of health services, education, gender equality, indoor environment, and several daily activities can all be upgraded with access to modern energy services. The importance of energy services for economic and social development is recognized in the Agenda 2030 for Sustainable Development, a set of 17 goals that list sustainable energy as a goal in its own right. The seventh goal focuses on a concerted global effort to ensure access to affordable, reliable, sustainable, and modern energy for all by 2030 and targets the elimination of energy poverty. To achieve this goal, proper energy planning should be carried out in order to match the supply with the growing demand in the most cost-effective way without compromising energy security and reliability of supply. In addition, energy planning is necessary if we are to move from centralized and expensive energy carriers towards fluctuating, decentralized, and cost-effective renewable energy production. Such modifications in the energy systems should be appropriately planned in order to have effective results. Until now, typical national energy system models have mainly focused on optimizing the bulk grid-generated electricity supply and have failed to model properly off-grid electrification. And why is this? Traditionally, energy system models require a plethora of input data and parameters in order to solve optimization problems. In order to keep models solvable in reasonable time and to reduce calibration and other input data requirements, most conventional energy system models consider spatially aggregated regions. However, the spatial dimension is important. There are several data related to energy consumption, distribution, and generation technologies, which comprise spatial attributes and need to be considered in order to calculate system costs and conclude to optimal set of technologies. These include information related to intermittent energy resources, power infrastructure, demand nodes, and economic activities. To illustrate, the wind power is determined by wind speed, which varies from one location to another. Similarly, solar power depends on solar irradiance, hydropower on rainfall patterns and topologies, the diesel cost on pump price and proximity to the pump. The simplifications employed by conventional energy system models call for more integrated and granular solutions. Ground-level geospatial data are of key importance to help identify effective electrification strategies and carry out regional access analysis. However, in more developing countries, as Jan mentioned, energy-related data in this level are usually scarce. And here is where geographic information systems can complement existing energy system models and help incorporate spatial and temporal dynamics to enable effective electrification planning while considering a growing mix of energy technologies. Geospatial analysis is an effective tool for supporting the planning, implementation, and monitoring of basic services delivery in developing countries. However, The use of GIS data and associated analytical tools to conduct strategic energy planning remains at the early stage. Yet, it has multiplied in recent years to support public and private sectors stakeholders in prioritizing and rationalizing decision-making related to energy infrastructure. There are several examples in the literature where GIS have been used as a planning tool for renewable energy infrastructure. More specifically, the identification of suitable locations and the mapping of renewable energy resources have been widely studied, spanning from local to national and regional assessments. However, most of these studies focus on renewable energy supply without considering the location-dependent energy demand and the associated cost of delivering energy services. Within a context where energy services are increasingly delivered in a decentralized manner and through non-state actors, energy planners and researchers gradually use GIS analysis in order to define national or subnational electrification plans and subsequent strategies and policies. But the majority of the previously developed GIS methods or tools have one or more of the following limitations. They only focus on how rural areas should be electrified and do not provide an overall electrification expansion plan for an entire country. They deploy a limited number of electrification technologies. They use a limited number of GIS data, some of which proprietary. They use a limited number of demand nodes, and they lack a grid expansion costing algorithm. And finally, they do not account for a dynamic change of the bulk grid electricity supply mix. Our objective has been to develop further the integration of GIS and energy planning, address the mentioned limitations, and provide insights on investment and capacity needs in order to provide electricity to the unserved. To do so, we have introduced a single cost model and integrated it with GIS, Geographic Information Systems, to calculate the cost optimal electrification mix based on electricity demand, grid connection characteristics, and energy resources availability in specific locations. This integration forms the basis of the open source spatial electrification tool, OnSSET, which we developed at KTH in collaboration with United Nations Department of Economic and Social Affairs, World Bank, ABB, our industrial partner, and other partners in order to carry out electrification analysis. OnSSET is an open source tool based in a GIS software and Python, which is an open source programming language. The code behind the toolkit, its documentation, and the datasets are publicly available. Further, OnSSET is a bottom-up optimization tool, which means that it is a technology-driven model, the objective of which is to increase access to electricity in the least cost manner. OnSSET has demonstrated the importance of opening energy modeling to the open source community, as it allows additions made by external contributors. It enables replication, which is one of the main principles of the scientific method, and users can repeat an analysis as the code and data sources are publicly available. And lastly, it allows users to carry out new applications and further develop the tool. How does OnSSET work? Covering unelectrified areas requires investments in new generating capacity. This can be added to the national electricity grid, which can be extended to these areas. Or, alternatively, new off-grid capacity can be added, operating either in form of mini-grids or standalone systems. More specifically, grid electricity is in principle generated in a centralized manner, usually from large power plants, which due to economies of scale are able to offer low generating costs. Electricity then reaches households through the transmission and distribution network in relatively low costs if the network is well developed. However, the expansion of grid infrastructure requires high demand levels to be economically viable. Mini-grids are an important alternative to grid extension. In this case, electricity is generated in a decentralized manner, usually from power plants with generating capacity up to a few megawatts. Mini-grids are usually deployed based on locally available energy resources, such as solar, hydro, wind, or can be based on commonly available fuels like diesel. Mini-grids based on renewable sources have usually high upfront costs, but no operational fuel costs. On the other hand, diesel generators are a mature, low-cost technology, subjected, however, to operational costs depending on diesel pump price fluctuation. Lastly, the third option available for electrification is standalone systems. These systems are usually based on local energy resources in order to produce a few kilowatt hours per day, able to cover the electricity demand of a single household. Standalone systems do not require transmission and distribution network, and therefore their capital cost depends only on their size. Now, how do we compare the options listed in the previous slide? The selection of the optimal technology for electrification in each location is based on the least cost option. In other words, the technology offering the lowest levelized cost of electricity generated throughout its lifetime is considered as the cost optimal option. OnSSET calculates the levelized cost of generating electricity for several electrification technologies based on electricity demand, grid connection characteristics, energy resource availability in specific locations. More specifically, OnSSET considers population density and distribution and electricity consumption levels to define the electricity demand. Based on the demand, the existing and planned power infrastructure and other economic activities, as well as resource availability, OnSSET runs an electrification algorithm. Based on the characteristics of each location, the algorithm decides whether a grid extension is the most viable solution to provide electricity to the unserved populations, or an off-grid solution should be preferred. New connections per technology are identified, as well as the required additional capacity and investments to reach full access to electricity. To synopsize, OnSSET aims at contributing to electrification planning approaches and energy resource assessments using GIS, Geographic Information Systems. A number of channels have been used to disseminate knowledge, including high-impact peer-reviewed journals and cutting-edge publications, such as the World Energy Outlook, the Status of Electricity Access Report, the Global Tracking Framework, and will contribute in this year's World Energy Outlook. Now, moving on to electrification pathways. The high interest in electrification, expressed from both academia, international organizations, and industry, created the need for developing an open online application named Electrification Pathways. Electrification Pathways, as Jan mentioned, is one of the 10 apps on energydata.info and is based on OnSSET, the modeling tool I briefly presented earlier on. In collaboration with World Bank and SMAP, we have developed this application that provides insights on electrification planning in 3 sub-Saharan African countries, Nigeria, Tanzania, and Zambia, and can be used by anyone with access to internet. The development of the interface involved model runs in powerful computers. Initially, the 3 countries were divided in squares of 1 square kilometer size. This gives us approximately 2.6 million locations in the mentioned countries. For all these cells and for various scenarios, we compare 7 mature electrification technologies and determine the least cost technology to reach full access to electricity, along with other critical figures that we will see in the next slides. The technology decision depends on several publicly available spatial parameters available for download on energydata.info. These include, among others, population density, distance from existing and planned transmission infrastructure, proximity to road network, nighttime light, as well as energy resource availability. The landing slide of the application introduces us to the importance of geospatial analysis in supporting electrification planning. Here we have 3 options. Option number 1 is to navigate through the model underlying datasets and explore the model outputs. Option number 2, access the code on GitHub, which is basically the online repository for storing, making, and tracking changes in the code. And option number 3, review the methodology, which was delineated earlier on, including how to use sections. Now, if we click on Explore the model, we are asked to select among the 3 studied countries. I'm going to select Nigeria. Once in the country page, a brief overview of the country status in terms of demographics, economy, and electricity access is provided. These data include current population and urban-rural split, the total area of the country, the gross domestic product (GDP) of the country, the population the total population that has access to electricity, as well as urban and rural electrification rates. And finally, the current electricity generation mix of the country. To illustrate, Nigeria, which is the most populous African country with above 180 million inhabitants, has the highest absolute deficit in electricity access, which exceeds 75 million people. Electricity is mainly based on natural gas and oil fuel power plants, and a significant share of the current production comes from hydropower. After this initial overview, we can continue to explore further the application. Starting with the left-hand side, the visualization displays buttons to select among 10 alternative scenarios defined by 5 indicative quantities of electricity consumption, tiers of access, and 2 diesel prices. The current one, which is a relatively low value, and the projected one, which is higher, and the default one. Also note that this is the diesel price in major cities, and this changes in remote and rural areas as we account for the transportation cost. As for the electricity consumption scenarios, the World Bank's Energy Sector Management Assistance Program has already demonstrated that people's access to electricity cannot be understood as a binary issue of connected versus not connected, and have thus introduced a multi-tier framework for electricity access. This defines 5 tiers of access, each tier involving progressively higher demands in terms of electricity delivery and hours of availability. These tiers indicate electricity consumption levels starting from providing electricity to light up a few bulbs, charge a phone or power a radio, up to providing electricity to a number of heavy or continuous appliances like refrigerator, washing machine, oven, etc. The combination of the population density and distribution that was shown in the previous slides and the electrification tier allows us to calculate the future electricity demand per location. It should be mentioned that these tiers consider a certain efficiency level, and energy efficient appliances might decrease the consumption level for each tier. Going back to the visualization interface, and after we have selected a scenario, we can choose among several datasets to be visualized. The default dataset is the least cost electrification technology. Just to remind you, the scenario that we have selected right now is high diesel price and tier 1, where we see the light bulb on the left hand side, on the left panel. Other datasets are grouped in 4 categories. Technology, which includes least cost technology, the levelized cost of generating electricity, investment costs, investment needs per capita, and added capacity. We have demographics related datasets, which include the population density, urban-rural split and poverty rates. Resource related datasets, which include solar irradiance, wind power capacity factor, and hydropower potential. And we have infrastructure datasets, which include distance to road and transmission grid network, cost of generating electricity using diesel generators. As you see in the center of the map, in the center of the page, there is a map of the selected country, while on the bottom you see a summary of the model results. This includes, for the selected scenario, the set of each electrification technology for new connections, investment needs, coverage area, and added capacity. Now we can further select a state or a district and explore electrification pathways for different scenarios. Let's select Oyo in southwest Nigeria. After we have selected a state, we can either select further a local government area for a district, or load all cells in state level. So for now, let's remain at state level and explore electrification mix for Oyo for the selected scenario. What's the currently selected scenario? Again, to remind you, this can be seen on the left panel. Now we are at the lowest consumption level, tier 1, and the higher diesel price. In this case, Half of electrification is accomplished by grid-based electricity for settlements located close to previously electrified locations and transmission lines, see dark green cells, while the rest will gain access to electricity, solar home systems, see light orange. When it comes to area, this share changes dramatically, and this is due to higher population density in areas with grid coverage. When the electricity consumption level increases to tier 3, grid extension becomes the most economic option for the majority of the newly electrified population. Standalone systems still play an important role, especially in sparsely populated remote areas. As the electricity consumption increases, mini-grid options start becoming favorable in remote areas as well. And this is even more apparent in the 5th tier, where mini-grid technologies become economically quite attractive while grid connections expand even further. It is noteworthy that even in tier 5, the highest electricity consumption level, standalone systems remain key to electricity access in remote and sparsely populated areas. If you scroll over specific locations, a table pops up on the right-hand side with information about the model outputs, such as the levelized cost of electricity and the investment needs, as well as some of the underlying datasets, such as population density in the selected cell, solar irradiance, wind power availability, proximity to road and power infrastructure, and so on, which can help us analyze why technology is selected as the cost optimal one. As I mentioned earlier on, the default dataset to be visualized is the least cost technology, but we have the possibility to visualize other model outputs. For example, the lowest levelized cost of generating electricity. This map shows the lowest levelized cost of generating electricity throughout Oyo. Costs increase from green to red. In this analysis, demand is population driven. So it is essential to map population density and distribution as this drives the demand. See, areas with higher population density, darker green, are more likely to connect to the main grid, and if the grid network is close enough. Staying in demographics, we have mapped poverty rates in district level. If at the same map, at the same page, we have a look at the investment needs per capita in district level, we can get an initial idea about the affordability perspective of electrification. For example, looking at Saki West district in Oyo, we observe that both poverty rates and investment, looking at Saki West district, we observe that both poverty rates and investment needs are on the higher side of the scale. This can help planners look at more affordable, lower electricity consumption scenarios, or potentially help design subsidy schemes. Moving on to resource availability, this is essential in identifying the cost-optimal electrification configuration. Here we saw the wind power capacity factor, which is a measure of assessing the wind power potential in a region. We identify also the solar power potential, as well as mini and small hydro power potential on a geospatial basis. Other essential inputs in the analysis are the road and transmission network, as this influence the cost of expanding the grid, as well as the cost of transporting fuels, in this case, diesel. Here we map the distance to the road network. Remember that the datasets shown here are also made available online at energydata.info. Electrification Pathways provides new electrification cost estimates that can be used to inform policymaking on electrification strategies and help bridge science, technology, and policy at different levels. So here we see the same model output, which is investment needs in different scales: local government areas, state level, and country level. Moreover, this tool can help planners and analysts identify investment and capacity needs by location and technology type. Some key takeaway messages regarding electrification pathways that I would like you to remember while leaving from this webinar. This tool introduces a complementary approach to existing energy planning models, which do not consider geographical characteristics related to energy, such as resource availability, location-specific infrastructure, and location-specific demand. Further, electrification pathways improve upon the oversimplified dichotomy between on and off-grid systems by comparing the two in cost terms after considering local energy-related characteristics. Moreover, this tool uses existing publicly available data, provides new GIS-based energy-related information, and is based on an open source and modular tool. Anyone with access to internet may navigate through and download the results of the electrification analysis. Note that the tool does not implement the identified strategies, nor does it provide the necessary finance, but it highlights before policy and decision makers are charged with the implementation of the 7th Sustainable Development Goal and allows the analysis of trade-offs between competing demands on financial resources and thus prudent prioritization of the available financial resources. I will stop here, and I would like to project my screen and show the application online and where you can actually find it. Can you please confirm if you can see my screen?
Yes, we can. And just a reminder to attendees to go ahead and enter questions into the question pane if you haven't already. Yes, we can see your screen.
Okay, fantastic. So we are here at the main page of energydata.info, where we see that the datasets have been growing from day to day. Yesterday it was 300, today it's already 308. And if we scroll down, we will be able to find the available applications. We see here electrification pathways. So you will click on electrification pathways, which is one of the 10 applications. We come to the landing page of the application. Previously, we selected to explore the model. We can also scroll down to explore, to go through the methods and read about the tool, read through the methodology, and see how we can actually, how are the scenarios built, how can we use the tool. It's basically what we discussed in the brief presentation. And finally, we can explore the model. Now we can select Tanzania instead. Again, the country overview, which is very useful if we want to get initial insights about the current status of the country with regards to electricity access and electricity generation. We have the possibility to select states. So previously we loaded all the states cell. Right now we can select further a district. And we see here that the majority or all new connections, in this case, the majority of the new connections actually in this case would be connected for a low electricity consumption scenario, would be connected with a solar home system. But if we are to increase the electricity consumption level, we see that grid starts penetrating and getting getting more favorable. While if we have the maximum electricity consumption level that is considered in this analysis, the majority of population that gets electrified should be through the grid. And this is again the least cost technology shown. We have the possibility to show other data sets, as for example, the investment cost. And we can scroll over can see the demographics in order to understand how population density affects influences the technology decision. So we see here that darker green shows areas with higher population density, and if we go back to our technology decision, we see that these areas are areas with high population density are grid connected. We can also examine how the solar irradiance looks like, which is pretty high in this district. And I'm trying to show the table on the right-hand side, but there is this GoToWebinar. Yeah, okay, so here you see the table I was referring to earlier on. So if we scroll over the district, we have the possibility to zoom in a cell and read all informations that we see on the data set. So technology, demographics, resources, infrastructure, the same information is available for each studied cell. So this analysis has been carried out for approximately 2.6 million cells, and we have this information for all these cells available on the tool and at energydata.info. So maybe I can stop here with my presentation. Of course, you can always use the help mode where you get some directions. So here we are technology. What does technology mean? Here, so technology represents the least cost electrification option at each geographic cell for the selected scenario, and this is the default mode, and so on. We can ask the help mode for explanations when needed, and we can take questions now.
Great, thank you very much. So, yeah, thank you to both of you for those presentations. As we shift to the Q&A, just another reminder for attendees to go ahead and submit questions to the questions pane. We have a few coming in already, but as they come up during the Q&A, feel free to enter them there. We'll also keep the tool up here in case there are any questions that we'd like to walk through live. All right. So the first question is just about what future expansion plans look like for the tool to other countries, or if there's other functionalities that folks are asking for.
Okay, so this analysis has been, or similar analysis has been carried out for all sub-Saharan African countries, 44 sub-Saharan African countries to be precise. In the same resolution. So these are available, but this would require an additional effort to have these additional countries on the tool online. When it comes to extensions of this tool, in general, I would talk about the electrification tool. We previously mentioned that this is the objective has been to provide electricity to unserved population, meaning provide electricity to residential side, to households. The idea is to add, and we are working towards this direction, to add other uses of electricity, which would ramp up the demand and influence the technology decision and the technology mix. And the incorporation of these other uses of electricity, so-called productive uses, constitutes a significant addition in this planning process. And these productive uses are usually the ones that boost income and welfare, and are typically in the sector of agriculture, rural enterprise, health, and education. Another addition is what you see right now is basically a snapshot in time. So you do not get an idea about how a potential electrification timeline would look like. To do so, we would have to determine priority areas that need to be electrified first. So this is another addition that KTH is working on at the moment, and a few more additions, but we can take more questions and we can discuss this later on. I don't know if Jan would like to add something on the specificities of our tool.
Yeah, so in terms of expansion and plans going forward, I think the point here was to demonstrate the value and the use of this kind of tools, as well as make the research done at KTH University available, more available and exposed. The results are pretty good from our point of view. It's being used, and by government is being quite useful for the 3 first countries. So there are discussion on how to perhaps take this work and expand it to additional countries with new data, as well as improving on its functionality, offering more functionalities for the users, perhaps additional scenarios, adding new parameters and data, as Dimitris was saying. So that's on our side. The good point is, by providing this tool as a true public good, meaning open source, anyone, any institution, any organization, or just IT proficient users or modeler can take it and adapt it for new countries at a very marginal cost.
Great, thank you both. The next question is for Jan, actually. You mentioned that the tool has already been used to inform policies and projects on electrification in Zambia, and that the tool produces rapid analysis in 1/3 of the time or so. The question is if you've had a chance to validate or compare the outputs of the tool with on-ground, more detailed analyses.
Yes, we did so. So quality assurance is, of course, key, especially when you're providing such a model and such analysis to government, and knowing that they will have an impact on their strategy. So we did, in fact, compare the result of the tool and the model with models that we conducted, particularly in Nigeria. And we compared the rapid assessment to an in-depth 1-year assessment with new data with customized modeling. And what we found is that the variations in results for Nigeria were of the magnitude of an average of 5 to 7%, with a maximum deviation of 15% compared to an in-depth planning exercise. So for us, that meant that as a first pass rapid assessment tool, this was highly satisfactory. So once again, what I mentioned in Zambia is that this tool is very useful for policy and strategy elaboration. It's once again a very quick rapid assessment tool that is provided for free, and as is. When you move into actual policy design, actual investment identification, program rollout, and later monitoring, you indeed may need to do an extra data collection effort, so enhance the modeling result by adding new data, especially geospatial data, meaning better map the grid, better map the settlement, verify the accuracy of those data sets, and you can improve marginally the result of the model, as well as refine the cost parameters that needs to be country specific and can be further refined. So once again, this is a first pass strategic level result, and it's an opening door to further planning to improvement, but at a later stage.
Great, thank you very much. Our next question is asking about how things are modeled out here. And the attendee is curious about how land cost is integrated into the modeling?
How land cost?
Yeah, land cost and access.
Okay. So the way land is accounted for here is basically by an input which is called grid penalty factor, and this refers to an additional cost which is added depending on the land use type, which comes from remote sensing datasets. So different land use types imply different grid, let's say, grid expansion costs. And this is the way land cost is being accounted for. So there is a matrix of information, a matrix of geospatial datasets that are used in order to calculate the so-called grid penalty cost. So one is the land use type. Another one is the distance from the transmission network, distance from substations, distance from the road network, and so on. And the topology, the slope, and the elevation. And we have, together with our industrial partner, who has several years of experience in the field, ABB, developed a table that is basically providing information about different classes of land, different classes of distances to the transmission network, come with different costs for extending the grid. And this is the way that land cost has been assessed. There is nothing else done in this case.
Fantastic, thank you. The next question is also for Dimitris. The tool provides a snapshot in the future and shows the cost optimal mix for 2030. Is it possible to look at a dynamic picture with an electrification timeline instead?
It is definitely possible, but as I mentioned, to do so, we would have to determine priority areas. So we would have to decide which areas need to be electrified first in order to limit the electrification expansion. And this is critical, and this is something that should be decided before doing the modeling exercise. One way of doing this is by limiting investments in areas that are closer to the road network, as the latter influences the prioritization of investments. And another policy can be reaching equity among districts or among the states or among regions. So maybe the government of Tanzania has as a plan to have the same electrification rate in all states to provide equity. So if this is decided upfront, the analysis, this can be incorporated in the model. The way we are working right now, and we are trying to be, let's say, agnostic of the prioritizations. Prioritization is by accounting for the road network. So the closer you are to the road network, the faster you will gain access to electricity. So yes, it is possible. You cannot see it in this particular application, but it is possible to incorporate this in an electrification expansion analysis.
Great, thank you. So you touched briefly on affordability, and one of the attendees is wondering if there's a way to understand whether or not consumers in a specific geographic area have the economic power to acquire electricity from the proposed sources that the model outputs.
Okay, so yeah, so this is a great point indeed, and in many of the capacity building workshops that we carry out or we participate, this the affordability dimension always comes. The affordability dimension question always comes up. So as I mentioned earlier on, the tool that we have presented today does not implement strategies, and it does not provide financing, but it can highlight challenges before policymakers are charged with implementation of the electrification. What we can do is to combine income data and willingness to pay for energy services, if available from household surveys, with the model outputs, which are the investment cost to reach access to a certain consumption level. And this will give us a first idea about the consumption level that would be affordable. And we can then have a look at suggesting subsidies either to utilities or to consumers, or even introduce innovative consumer financing models such as the pay-as-you-go model. So imagine that you are examining how much it would cost to provide access to provide the highest electricity consumption level to a village. And in the same area, you know, you have information about income levels or information about willingness to pay for energy-related services. If you combine the two, and you iterate, you know what is the consumption level that would be affordable for this particular village, because different consumption levels come at different costs, different investment costs, different costs of generating electricity, and so on. So if you have this information and you overlay these two geographic layers, the answer you will get, the insight you will get, not answer, you will get an insight, is very powerful.
Great, thank you. That was very helpful. Another thing that you touched on briefly, I wonder if you could expand on is, you know, the tool identifies the cost optimal technology mix to provide electricity for households. But can you talk about electricity use in other sectors other than residential?
Sure. So again, we have the productive uses of electricity that boost income and welfare. And again, we are working on designing and adding functionality in the developed tool with regards to these other uses. So for example, we are trying to identify where we might have potential demand for agriculture, or how much would the electricity demand be for community services such as schools or health clinics, or even public institutions and facilities. These for community services. And then again, if we go back to income generation, productive gain activities, apart from agriculture, we are looking into extending or providing electricity to industrial uses such as mines, quarries, and other commercial activities such as small to medium size enterprises and so on. So if there is this information available on a geospatial basis, and there are these data sets available online, we can incorporate those in the model and see how this productive use of electricity influence the optimal generation mix, and the investment needs to provide access to electricity.
Great, thank you. One more question before we turn to any closing comments you might have. Is it if you've gotten any feedback so far on sort of who's using the tool and how, you know, between those three different options, you know, of accessing the code itself, looking through the model, searching by country, and if you haven't got any feedback yet so far, you know, how you anticipate, sort of who you anticipate using this the most and how.
So the tool has just been launched publicly, so we'll wait to hear feedback from users as it gets used. But in the meantime, we did a soft release a couple of weeks ago, and it's been used, as I was mentioned, by government. So primarily, the tool is aimed to inform government and provide them with a rapid assessment planning tool to inform their electrification strategies and plans going forward. And that was the case in Zambia. Once again, it was very well received, integrated in the strategy elaboration process, and is leading the way for additional, more granular, different scenario type of analysis as a follow-up. Interestingly, it was also provided and made available prior to launch to a couple of off-grid companies that used it to identify what could be their market potential in a given country. And they were very pleased with the result, corresponding, in fact, to the figure that they had previously estimated on their own. So it can be also used by private sector working on access in country to get additional data on, for example, the number of households, potential investment costs, and priority areas, specifically looking at the underlying layers that can be displayed on the app.
Great, thank you. Yeah, and thank you both for that, both your presentations and that very informative Q&A there. I'll turn it to both of you if you have any closing remarks to make before we close out the webinar. Maybe Jan and then Dimitris, if there's anything you'd like to add before we close.
Thank you. I'd like to thank you guys and the Clean Energy Solutions Center for organizing this webinar. In terms of closing remark and more broadly than this tool, I hope that people will use this tool and find it useful. We look forward to receiving any feedback, any potential opportunities to collaborate in making this, taking this a step further. But more broadly, and on the open data and analytics agenda, the World Bank has taken a partnership approach to this agenda by providing an open data platform that is not only for the World Bank, but also for various organizations and individuals to contribute. So as my main closing remark, I'll encourage participants and stakeholders to please reach out to us to contribute to this initiative if they want to and can. Our address can be found on the website directly at energydata.info. Please shoot us an email and we can kickstart the conversation and hopefully collaborate further on this agenda. Thank you.
And then from my side, I would like to add on Jan's closing comments that you have now seen one, let's say, application of the electrification modeling tool. If you are interested in seeing the code itself or exploring other applications or other projects and reading through the methodology and through the peer-reviewed publications, you are welcome to visit our website at www.onsetws.org, where you can go through lots of material as well as through the code itself. Again, this is a very powerful application that doesn't provide the final, let's say, numbers, but it provides significant insights about electrification planning. And we also get a very good idea about which data sets are important for us to gather while carrying out such an analysis. So, for example, you see here how important the transmission network and the population density is when we carry out such an analysis. At the same time, we talked about affordability. So if we have information about the willingness to pay or from household surveys, and we overlay this on a geospatial basis, we will manage to be able to be one step closer to address the affordability issue and provide affordable access to electricity. Because access to electricity and access to electricity and electricity supply in general cannot be sustained without development, and the other way around. Development cannot happen without access to electricity. And on the development side, again, it would be very important to incorporate the other uses of electricity that boost income and welfare. So again, it was a pleasure being hosted here. Thank you.
And on behalf of the Clean Energy Solutions Center, thank you as well again for these presentations and that Q&A. And thanks as well to our attendees for participating in the webinar today. We appreciate your time and hope in return that there is some valuable insight that you can take back to your ministries, departments, and organizations. We also invite you to please inform your colleagues and those in your networks about the Solutions Center resources and services, including that no-cost policy support through our Ask an Expert service. Please check the Solutions Center website if you'd like to view the slides and listen to a recording of today's presentations, as well as previously held webinars. You'll also find information on upcoming webinars and other training events there, and we're posting webinar recordings to the Clean Energy Solutions Center YouTube channel. Please allow about a week for the audio recording to be posted there. And finally, I'd like to kindly ask you to please take a moment to complete a short survey that will appear when we conclude the webinar. Please enjoy the rest of your day, and we hope to see you again at future Clean Energy Solutions Center events. This concludes our webinar.